No, it's just like chemical storage and safety factor. So is this ringing a bell? A little bit about what we spoke of yesterday? You were shaking your head, all right? It's a good like 10% of the class. All right. So the big point is really like you can have something that is truly an acid and then truly a base, and then you can have ions that behave like an acid or behave like a base with water. So that's what we'll call them acidic salts or basic salts, or a acidic ion or a basic ion, not because it's an acid or a base, but because of how it behaves. So that kind of goes back to your definitions again with Bronsted-Lowry, even Arrhenius, and Lewis acids and bases. I'll touch base on just a little bit towards the end of today, if not Monday. But if it's behaving like an acid, it's definitely donating H+, and it's behaving like a base, it's accepting H+, and with that, as it's behaving or interacting with water, it's producing either hydronium or hydroxide ions in water. So the parent acid and parent base language I was using yesterday is how we'll kind of continue today. And then that will kind of hit the rest of salt hydrolysis that you guys need to handle in terms of like ice balances. So as a quick reminder, and I keep repeating this because it's easy peasy multiple choice questions get correct or incorrect. The stronger the acid, the what? The conjugate base. Weaker, so that means that alright, well, hold on. Usually you just hit it and it handles itself, so we're going to try this real fast. Okay. Okay. So the stronger, the weaker. We're just going to do this for a hot second, okay? The weaker, the conjugate base, and then the stronger the base, the weaker the conjugate acid, right? And so anytime you're having a strong substance forming a weak substance, that weak substance is not going to revert back to reform any of the original reactants. And then kind of now dealing with the salt aspect versus the acid or base aspect. Salts that contain a cation from a strong base, but an anion from a weak acid, which then therefore it is the conjugate base, is a what type of salt? Acidic, basic, or neutral? Say again? Basic. Okay, so the cation of the strong base is really the dead giveaway. It is basic because the conjugate base, or the conjugate base will form OHs in solution, and that's really what's telling us that it's going to be therefore basic in the end once it's undergone hydrolysis. And then salts that contain cations, the conjugate acid of a weak base and an anion from a strong acid are what? Acidic, and that's going to be because the what's the important part of the salt? The cation or the anion in this case? The cation, right, is which has the conjugate acid of the of the weak base. So they use acidic because the conjugate acid forms what? Say again? Hydroniums in water. And so we're really not focusing on the ion that's not really appreciably interacting with water. We're looking at the conjugate of whatever it is that's going to interact with water and either form hydroxides or hydroniums. All right, I'm going to go back to check homework just so I can figure out what the board's going to decide to do here in a second. So, okay, so let's go here. I know the first, like, how do we feel like 43, 45, 54? Shake your heads, people. Yeah. 45C. I'm going to have to pull up a textbook here. Do you have the, you have it? Can you ask me, or can you tell me 45C? F minus in hypochlorite. Okay, so just stronger base. Okay, so for the stronger base, it's going to be the one that is able to accept an H plus easily, and so the stronger base can be, we'll talk a little bit more about bond strength and then also anion or cation size. But if you have a larger anion, because fluoride's really small, according to the atomic radius trend, which is getting to be more cumulative than we want to right now, it's fluoride is smaller than than hypochlorite, so the larger anion will have less attraction for its H plus back. So a big ion has the nucleus really in the center of it, so a large anion can't attract the H plus back very well. So a smaller anion definitely can. So the stronger base would be, should be hypochlorite though. But it's asking about the stronger conjugate base or stronger base. What is it? Does it say? I don't have the textbook in front of me. Okay, I'll come right back to that for you. I would like to go to the K or PKB one. So that was 91. That was the specific one I wanted to review with you guys first. And I know your KBs in terms of like actually writing the reactions, you guys were probably okay with that. So one second. Okay, here it is. Caffeine. This pen is already goofing up. Okay. So we have caffeine, and given the fact you have a relationship between pH and H plus, which the relationship to go between the two is just log, and then opposite of log is 10. So if you have pH, you can get to H plus by using 10 to the negative pH. Same thing applies for Kb. If you have pKb, you can do 10 to the negative pKb to get just what Kb is. So 10 to the negative 10.4, you get the Kb value to be 3.98 times 10 to the negative 11. So that was the part that you really had to approach first, because otherwise you could not attempt the problem. After that, given caffeine's formula, you get 10 to the negative, it's 10 to the negative 10.4. Oh, over there, no. I think it's a negative 11. It's shaded over there. So once you have caffeine's formula, you're going to make it act as it should, and it mentioned Kb, so you're going to make it act as a base for now. So you're going to donate H plus over, make your cation and then your hydroxide, and then they told you, milligrams, but you guys can get that to grams, from grams to moles, and then go to molarity given the information given. So you should have achieved molarity to be about 0.00234 molar. And so I plugged my icebox all kind of in one, versus stacking it in 3 rows. I just kind of put it all in one. So that's why I have initial, and then minus X, and then the 2 products you add your X's to. So setting up your expression with your products over your reactants, and the Kb value you just calculated, you can then plug in your X's, show your Kb value, and then I include the subtraction of X, but then say, okay, I'm going to neglect it. That's you showing me that you're neglecting, so try to incorporate some style like that. And then once you're plugging and solving, I just went ahead and isolate X squared and then square root, so you get approximately 3.053 times 10 to the negative 7 molar, which is the X value, which is the ion of interest was the hydroxide. So then from our hydroxide, what do we do? Yeah, find pH from POH. So in doing that, POH was 6.57 or 6.515 for the POH, and then backing that up to pH. It's pretty weak, like super weak, and it's not really because it's a weak base, it's because it's weak and it's dilute. So that combination makes it really close to 7. And then there were 3 sig figs on the back side of the pH because of the 3 sig figs that were given in the milligrams. So who kind of figured out pK, or what to do with pKb on their own? Once you know your mathematical relationships there, then you were able to apply that. Okay, so the other one, whatever the next one is, 90 past 91, 94. Okay, so being given the pH, and then it asks for you to solve. What did it ask for you to solve for? The KB. Okay. So how did you guys attempt this after you utilized the pH? Okay, so we know you're setting for a nice table, but what do we do with this information? Because pH is going to give us POH. TOH is going to give us OH concentration to be 1.6 times 10 to the negative third. What do you do with that? Yeah, okay, so we plug it in for X and we roll. So there's no, we know that means equilibrium value of OH, and so once we know the equilibrium value for OH, we know the other ion, and then we know how much the subtracted version was. So we have the whole complete icebox, we can complete the icebox. So I put BOH, but you could just put B as your generic base. So as long as your ions formations are right. So you plug your initial, those are your two changes, which also applies on the reactant side. And then setting up your KB expression, which I encourage you to always do, even if you don't need it, just so you're practicing it because brain farts occur. So plugging your two products over the reactant equilibrium, you do have to subtract the X. Since you know the X, you can't neglect it. You have to subtract, and you should get a KB value of about 2.06 times 10 to the negative fifth. Yeah.
What exactly do they do?
They'll go by based on sig figs. So this, was it 2 sig figs? So that should be 2.1 times 10 to the negative fifth. Because this is 2 sig figs in the pH, so the concentration of OH should be to 2 sig figs. And then so forth. The KBs would be to 2 sig figs. Oh, they would give you some flexibility. They have a range they can do, but they don't always publish that. It's sometimes different for different questions. Okay, so in terms of setting up the ice boxes and setting up with KBs, you guys are okay? Okay, let's go to salt hydrolysis again, and then we'll come back and check some more questions. Because I had another one on, someone asked me yesterday about the percent ionization and what to do with that, so I can come back to this one in just a second, okay? So I wanted to do that, but yesterday we didn't quite finish, and I don't want to put us through that again. So, okay, so I want to go through a couple of examples. But I'm telling you the types of problems first, and then I'm going to tell you for you to decide your own types of problems, because if I tell you the type of problem, it might be quickly, you might figure out how to approach it, but you need to find out how can you determine the type of problem, and then from there go with your rules and how to approach it. So we're dealing with a salt. How do I know this is a salt? 2 ions, right? So it's 2 ions, which are non-H's and like OH's. So we know it's a salt because it's basically an ionic compound. And we know it's a salt of, in this case, sodium ion, which came from sodium hydroxide, which is a strong base, and cyanide, which came from cyanic acid, which is a weak acid. So we know it's a salt of a strong base and a weak acid. So from that, the parent acid being weak and the parent base being strong, we already know baby salt's going to be what? Basic. So that prediction power allows us to check our work later. So it's nice to write that up front so we can compare later on. So if we have these 2 ions, we have to choose which ion is appreciably going to interact with water to produce ions. So we write them both out. Okay, we add water to both because it is salt hydrolysis, meaning add water. What does sodium ion form with water? Sodium hydroxide and H+. And then we immediately see sodium hydroxide and we say to ourselves, so this is a strong base, so it ionizes, right? So if we ionize into sodium ion, hydroxide ion, and then also H+, the hydroxide and the H+ get right back together and they reverse this reaction. So we have a strong reverse reaction here. So instead of actually writing this all out and thinking about it, now, if you start to see this up front and you're like, oh, I'm going to form sodium hydroxide, I already know this is a what reaction? So no reaction, right? So it's not truly reacting. It's going to go make its ions and reverse right back. So I'm going to put NR here to indicate that's in a reaction. That's not our most important half reaction, you can say. So then cyanide will interact with water to make what? Cyanic acid and hydroxide ion. So if you prefer to write water like HOH, you can see that replacement reaction occur a little bit better. So the H goes over here and bonds with cyanide, leaving hydroxide left over. So this is going to be an appreciable reaction because this is a what? Weak acid, so it doesn't make a large attempt to reverse itself because it's not going to strongly ionize at all. So it's going to stay in its form, and then hydroxide also stays because there is no appreciable reverse reaction. So now we can apply the molarity given and actually run an icebox. So first, before you do that, would you consider this a conjugate acid or a conjugate base? Loud and proud, come on. Conjugate base, because it's from a strong or a weak acid, so it is a conjugate base. Is it a strong or weak conjugate base? Strong conjugate base. And so that is something to I'd use as a comparison too, because the stronger the conjugate base, the more likely it is to react with water, the less likely this is to react in the reverse manner. So we're putting 0.25 molar, 0, 0. I'm going to run through ice. So what was it? Second? Oh, 0.25. Thank you. So we're going to run through ice. I was like, I've already fixed this one. So subtract x, add x, add x. And this gets tedious, so like I kind of truncated it down to just one line. You can do that yourself as well. Okay, how is this ion behaving? How is cyanide behaving? As a base, because one, we just labeled it as a conjugate base. We see it's making hydroxide. Automatically, you have to apply a K what for this problem? KB. But we have to find the KB from anybody? Well, we use KW, but we also must have what? Ka of what though? Cyanic acid. So you'll find KB from Ka for cyanic acid, because this counter ion, so the conjugate base, is coming from cyanic acid, so that's your comparison. So what is cyanic acid's Ka? Ka is 6.17 times 10 to the negative 10th. You guys gotta be louder for me, sorry. So this is negative 10. Okay, so find your Kb. How would you do that? I heard use Kw, but give me more. Okay.
Kb equals Kw over K.
Good. So Ka times Kb is equal to Kw. So to rearrange that, we're solving for Kb, Kw over Ka. So 1.0 times 10 to the negative 14th divided by 6.17 times 10 to the negative 10th. And if you can, before you maybe plug in, can you estimate? You can at least give me an estimate for the exponent. So approximately 10 to the negative 4th. So it's going to be a higher value. All right, so what is that? Calculators. I can calculate too, but I'm depending on you. 6. Okay, 1.62 times 10 to the negative 5th. So that little estimation helps us make sure we put it in our calculator correctly too. So this is KB. And so now that we have KB, we're able to plug in and run with it using our KB expression. So what is our KB expression? Get me started. Well, give me the expression just for now, and then we'll plug in those values, like the actual expression with the ions. Okay, so molarity of HCN times OH minus over cyanide. All right. Okay. And then we say X, because those are our two products, over what? 0.025 minus X, but then immediately you're showing me what? Attempt to neglect X. And that's just really all you need to do. Don't get too fancy with it. And we end up setting this up to or equal to KB we just determined, and then solve for X. Go ahead and solve for X if you haven't already. guys are? 6. 10 to the negative 4th molar. So this is equal to what ion of interest? Concentration of hydroxide. Good. So that's why it's nice to write it here, so you can actually make sure you're in the right place. So here's our X. Can we run a quick 5% rule? Does it meet the requirements? 2.5%. Yeah, so yay, 2.5%. It's just nice to stay in that practice so you're always checking. So now we have this, and we're solving for pH of this salt and water. So now that I have this concentration, I can use the heads to find pH by doing what? Say again? Okay, so 14 minus negative log of the OH concentration, right, which is that right there. So 14 minus a negative log of 6.36, which before you calculate, if you haven't already, can you give me an approximate for the pOH using this exponent up here? So between 3 and 4, right? So we know that the pOH is between 3 and 4. So let's just say 3.5. Let's just kind of have it. So if that's 3.5, then what's the pH? 10.5, right? So what is it when you calculate that? 10.8? Let's go correct sig figs. You said 10.8. So how many sig figs do I have in this problem? Right, there's 2 sig figs. So then how would this be down? How would this look down here? It wasn't like 7 something, right? It's 8 here. Okay. Okay, so then in our pH there are 2 sig figs post decimal. Alright, so which part is really hard about the salt hydrolysis? The bottom part's like second nature to us, right? We know how to run this. I think the first part is the thought process that goes behind determining which ion is important. Okay, so let's do another one like that. Can I move on? Yeah. If you have an ion and it makes a strong blank, like strong base or strong acid, it just reverses itself because strong stuff will ionize and it won't stay as a product. They just rearrange themselves back. So the hydroxide ionizes off, bonds with H+, and comes together to make water, and then sodium ions left over again. Anytime you make something strong, it doesn't stay. It wants to dissociate again. Okay, I'm just going to talk to you about this one first. This is a sodium ions coming from sodium hydroxide, which is a strong base, and then bromide is coming from hydrobromic acid, which is a strong acid. So automatically we know that the strong and the strong parents create a what salt? Neutral salt. So we know this is neutral, and we would never actually say the 2 ions come from strong acids and bases, therefore is a neutral salt. That's what we're thinking, because that's kind of how we started off at honors camp thinking about salt hydrolysis, and now we're using some of those same principles. But the way you would explain this is you would say the sodium ion and the bromide ion react with water to make equal quantities of what 2 ions? Yeah, hydronium and hydroxide. It's just because of the nature of how those ions are created in an equimolar fashion. So we make sodium hydroxide and H+, and then hydrobromic acid and OH-, though this is not a very appreciable reaction because it doesn't occur in high quantity, these are still going to be one present from the minor amount of these ions that do actually react, plus this is happening in water, right? What does water do by itself? Auto-ionizes to make equal quantities of hydrogen hydroxide. So we don't really approach it from the salt aspect on neutral ones. We approach it from more the water aspect on neutral ones. So I would say this is a neutral salt because in undergoing dissociation, there's going to be equal quantities of H+ and OH-. So water will dissociate to form equal quantities of H+ and OH-. That's really the part that is going to control the pH because the salt doesn't make appreciable amounts of ions anyhow. Good with strong? We'll practice with the strong a little bit more, but it doesn't require any heavy math. Okay, I want you guys to attempt this one. I've already told you what kind it is, but I want you to attempt it. To make this a little easier, if you're wondering what are you wondering?
And,
What value do you need from me?
okay.
You need the Ka? You could find the K, I mean, because truly, this is acting as a acid, right? It acts as acid, so get Ka from, well, you won't find ammonium as an acid in the Ka chart because it's not truly an acid, it's just an ion, right? So I would normally find the Ka from a published value called the ammonium or ammonia.
Ammonium.
Oh, so normally you won't, that chart's something I found that's got very, very inclusive data, but normally you would find, or you'd be given a Kb for ammonia. So that's what I was trying to get you to see. I would give you the Kb for a substance that is truly a base, which is ammonia. It's 1.8 times 10 to the negative fifth. So this Kb is what you'll use to actually find your own Ka, because your chart, you won't have that chart on your test, and it won't be data that's actually provided for you because it's not truly an acid. So it acts as an acid, so we're going to get Ka from Kb for ammonia. Yeah, this is a good chart, but you have a lot of information, but it's not very. You won't get that kind of data on a question necessarily. But there's your Kb. I would give it to generally because ammonia is a base and ammonia has a published Kb. So any guessers for X? Times 10 to the 7th.
Sorry.
It's okay. You're good. I make mistakes. All right, so this is a molarity for what ion? All right, so now we have the hydronium or H plus concentration, and I can find pH very easily with that, which would be, give me a guess first before we hit the calculator. 5 point something, right? Maximum of 6, because it has to be between 5 and 6. The exponent gives you the ultimatum. And then this is this closer to, do you think it's going to be closer to 5 or 6 based on this initial value? Closer to 6, because this is a lower value, right? If it were a high, like 9 times 10 to the negative 6, that'd be a higher value, which means it's got more H plus, which means pH goes down. Because remember, it's inverse related. High concentration of H plus, pH goes down. It's a lower concentration of H plus because closer to the one side, so pH goes up. So it's what? 5 point what? 6.3. Okay. 2 sig figs all the way, right? We take that, we make that 2 sig figs on pH after the decimal point. All right. We said, oh, I did not show my prediction. Up here, we said that ammonia came from a strong or weak acid or base. Ammonium came from ammonia, which is the weak base, and chloride came from HCl, which is a strong acid. So between that comparison, you already know you can predict the salt's pH is what? Acidic, right? And then we double checked, and as we go through calculation, we've now shown, is it acidic? Yes, it's not that acidic, but it's acidic. Yeah. So so this H right here donates itself to water, forming hydronium, and it leaves behind a non-charged species, ammonia.
Is that just like H plus?
It's technically, like, if you wrote H plus over here and you wrote water here, you technically be wrong. Since we're working with water all the time, try to hit hydronium, but you'll see a lot of times with my acid problems, it's an acid. I just take the acid I've associated, make H plus in the ion. I don't always show water, but with bases we generally do because there's that's how you're going to show like the H plus being donated to form hydronium. Okay, are we okay? All right. So the last one I want to show you is this one. Okay. So write down ammonium acetate, and then predict what you think potentially the acidity of the salt would be. Any predictions? So we're saying close to what? Possibly neutral, possibly, right? Because it's a combination of ions from what and what? Weak and weak, right? So we know for strong, if it's a strong combo, it's definitely what? Neutral, because water is the one that's doing the damage for ions. If it's a weak, strong combo, it's going to side with the stronger side. But if it's a weak combo, we can't always assume it's just neutral, because we actually have to compare Ka's and Kb's. It's going to be close to neutral because it's all weak, but it might be a hair bigger than 7 or a hair less than 7, therefore we would then call it acidic or basic. So we must take ammonium and add it to water, and then acetate and add it to water. Okay? So how is ammonium acting? As an acid or a base? As a what? Loud and proud, people. Acid. You should be able to figure that out at this point, because you've never seen NH5 2+, ever. Like, it's not going to take on another H+. The only option it has is to donate an H+ to water to form, leaving itself with no charge and it being ammonia, and then forming hydronium. So since it's acting as a what again? So act as acid, I need to find Ka from who's Kb? Say again? Ammonia is Kb. Kb for ammonia. So let's go ahead and do that. I already told you that ammonia is Kb, but I'll tell you it again because, you know, lots of numbers here. Kb for ammonia is 1.8 times 10 to the negative fifth. Okay, and we actually just did a problem with this, so quite easy to show that worked again. so that was 5.56 times 10 to the negative 10. So this is the Ka for ammonia. With me? So we know that it has to come from the Kb of ammonia because that's its counter ion. Okay, so then acetate, the other one here, just trying to move this out of the way. Alright, well, I'm just going to, I somehow copied that, okay. Alright, so acetate forms what in water? Acetic acid and what? And hydroxide, good, because this H plus gets donated, so water's acting as the acid, so therefore the acetate ion's acting as the base. So we must find Kb, because it's acting as a base, from Ka of who? Acetic acid. And I will tell you the Ka of acetic acid is 1.8 times 10 to the negative 5th. What? It's the same thing. So we must still show our process of finding Kb for the acetate ion, which when we calculate Kw over the Ka value I just told you, we get 5.56 times 10 to the negative 10th again. This is the Kb for acetate. And I'm just labeling this really clearly so you understand like who's the Kb applying to and so forth. So here's the predicament. If your Ka is larger, you say the salt, whatever the salt is, would be acidic in solution. If your Kb was larger, you would say the salt was basic in solution. But we have a situation where they're the same, so this truly is what? Neutral. So that's your rule of thumb for weak-weak combos. There you go. If Ka is equal to Kb, it's neutral. It's a neutral salt. If it's Ka's, the Ka of the ion that's acting as the acid, that's what we actually still have to derive them. We can't use the Ka's and Kb's given. We must derive the new Ka's and new Kb's. It's going to be an acidic salt. And if Kb is greater, then it's a basic salt. So salt hydrolysis really only has like that one extra thought step that happens before the ice table, and that's the part that you have to kind of talk to yourself on. So I'm going to give you guys some time to let this sink in some more. Pull up your salt hydrolysis problem set, which is in your packet. And specifically, I want you to attempt the salts right now. I might need to look over some sugar to see the problem. So I want you to start with 1, 5, and 7. 1, 5, and 7. Start with those, and then the other ones are going to be 1, 5, and 7. Yeah. So I know not all of you got to all of it. So I'm starting off with the salt. So 1, 5, and 7. I know.
1, 5, and 7.
Yeah, but I want you maybe didn't get a chance to finish the salts, which are the ones that we didn't practice a lot yesterday. So that's why I'm going to start now.
1, 5, and 7.
Yeah. I'm just giving you some time to let it sink in. If you've already attempted these and you're awesome, move on to either practicing your FRQs for tonight or create an equation writing problem set. So first we're going to go on. So this is only did one yesterday, but I figured I should be able to do two.
So I just was looking at the thing at the top, which one's going to be strong, so it's trying to make sure that it's neutral. So I'll show the one, so like it's just left, and then I'll do like the whole thing instead of like I won't just do the nature, I'll do like. Oh, okay. Okay. So just exclude that. Okay. So just alright.
So we use like
That is really we're just behaves. This is a secondary plus. You shouldn't need to start. No, just make sure you're setting up. It's actually more than plus. And we've never seen anything like it. We kind of shared this with you. And this one doesn't have an extra plus. So it's going to have an extra. So it's going to take on an extra. And it does have like so that's fine. And then this way, maybe like two classes. This leaves over leftover, so one of just goes here, right? Leaves behind OH minus. So it's going to be OH minus right there. Because that's your right. So I was you have to base it on the ion. The ion is producing OH and it's accepting it again. And I'm just going to correct my thing just again. So if you have an OH, and you correct that left behind OH. That's what you do. Yeah, All right, take one more minute wherever you are. Is there a value you need for anything, like a KB you might need? I know you have your list of KAs and some, but other things, but do you need KB for anything? If you're looking ahead? Obviously, you should be asking for a KB of a base, yeah. Yeah.
When it's the next one,
pH 7, it's 0.00. You know ammonia is KB now, and that's like the general one I use a lot. So the KB for ammonia is again what? 1.8 times 10 to the negative fifth. Ammonia's KB is 1.8 times 10 to the negative fifth. I think that's the only one you need because all of your other KBs will be calculated from KAs.
So if it's active in the acid, it's Ka.
You need to find the Ka from its KB. From the base's KB.
So it'll always give you the opposite formula, just so you do that.
No, I mean, you have to find the opposite because it's acting in opposite fashion. If they have ammonia's KB published and then you have ammonium, you must find the Ka of ammonium. If they have
But like they'll typically do that where you have to divide 1.0.
only if it's salt hydrolysis, yeah. All right, so I know you're finishing up a problem. We're doing diprotic acids today as well, so that we're not pushing stuff next week. Stuff. So I'm going to go ahead and put up 2 questions for a quick discussion, and then we are rolling into diprotics. In your packet, I'm going to be approaching some diprotic stuff, which is right next to the salt hydrolysis problem set. So it's right next to salt hydrolysis problem set. There's a bunch of like empty spaces. So first question, and this is a little bit from your reading, so just we're going to fill in the blanks here. For diprotic acids, subsequent Ka values get larger or smaller? Smaller, because are they weaker or stronger acids as they deprotonate? Weaker, right? Smaller Kas are weaker. So, because weaker acids. So your Ka1, which is showing the first deprotonization of a diprotic acid, is larger than a Ka2, and if you have a triprotic acid, it's going to be greater than the Ka3. So you even see some of those on your tables, Ka1, Ka2, Ka3. A lot of the acids we've been dealing with so far are monoprotic, so they have 1H+, that's our acidic acid, or acidic hydrogen, but some of them like sulfuric acid, phosphoric acid, carbonic acid, and so forth are going to have multiple Ka values. And then, reminder, and this is related to this, it is more or less difficult to remove an H+ when you're creating a highly charged anion. Highly charged anion would be something like sulfate with a 2-, so meaning high charge of a negative. It'd be more difficult because you're taking sulfate, or you're forming sulfate from maybe bisulfate with a 1- charge. So a 1- charge already has a strong attraction to a plus because negatives and positives attract. So if you're trying to take this H+ off, you're going to have a pretty difficult time. It will not do it willingly, so your Ka value is going to be small because it's not going to dissociate in an appreciable manner. So this is not going to form in a high amount simply because the H plus will be attracted to its negative charged ion, and then thus forming the highly charged anion will be more difficult. So this is what we're kind of talking about, but now applying it to a to a diprotic example. Thumbs up when I can move on. But these are like the two big concepts we're talking about with diprotics. Okay, so with respect to sulfuric acid, we know sulfuric acid is a strong acid. Yes? So it's one of the weirdos because it's diprotic, it's strong, but then everything after that it forms is weak. So most polyprotics, most of them that we deal with are weak, except for sulfuric. And since those other acids are weak, they're going to form a little bit of their products in the first deprotonation, and then they're going to form even less and less and less of their products in the subsequent deprotonations. So the process of removing H plus, removing H plus, removing H plus makes less and less and less of this acidic ion in solution. So usually we say the most significant production of acidic ion, so hydronium, is in the very first deprotonation. And then after that, it makes such a minuscule amount of hydronium that we're not too concerned about it because it's not going to make a significant impact on pH. So usually the first deprotonation is the part that's going to really control the pH of that particular acid. So I'm going to show you the successive reactions for sulfuric acid, and I'll show them on the board here in a second, but I'm going to finish let you guys write down what you need to. So here's sulfuric, H2SO4, and I can add it to water, and then what does it produce? Showing one H plus being donated at a time. H, SO4, say again, minus, you must have your charges, and H3O plus. Okay, so that's called Ka1, or it will show that it will express the value for Ka1 because it's the first acidic deprotonation. So now that this has done its deprotonation, and actually, my bad on the double-headed arrow, this is a what? Strong acid, so we show a single arrow there. Now this Ka1, look on your Ka sheet. What does it say for H2SO4's Ka1? What does it say?
There's no value.
There's no value, right? Some of them will say like very large. So very large is just indicative of a large Ka value, which means all products are favored. So this is 100% forming these two ions. The second part of the process would be the H-SO4 minus, which is the conjugate base of sulfuric acid. It can undergo I want to say deprotonation, but that's wrong. Deprotonation, yeah, that's the word, with water. So what does this form? Sulfate and hydronium. And this would be the Ka2. This is actually a larger Ka2 value than most other things. What is it on your paper? 10 to the negative 7 second, right? So that's actually pretty large compared to a lot of the Ka values we've been working with. So there's no more H's to be lost from sulfate, so there's no Ka3 or Ka4 or anything like that. So we are basing it on the number of acidic H's that the polyprotic acid has. And so that's kind of what this is showing. But it just doesn't have all the ions involved. Are we okay on these two? Okay. So we're going to calculate now, but we're going to use phosphoric acid, the pH, and then all the ion concentrations. So once I do this once, really you can apply this to any polyprotic, but it just takes a minute because it's a little long. A couple of ice tables, here we go. So phosphoric acid, right? Want to know the pH. So basically that means to find what? Concentration of hydronium. Okay, so the first reaction, the first deprotonation is going to be the most appreciable amount of H3O plus. So let's do that one first. So phosphoric acid plus water makes what? Don't have to name it, just spell it out for me. H, PO, 4, 1 minus, and hydronium, okay? And this will be Ka1, which is 7.5 times 10 to the negative third. Okay, so we have a concentration given, which was 5 molar. So where am I putting that 5 molar? Under the initial acid, okay? So let's ice it up and ignore water. 0, 0, both of the ions initially. Subtract x, add x, add x. So this is like deja vu, we got this. So 5.0 minus x, x, and x. And this is our equilibrium value, or set of values. Now I need to set up my Ka1 expression. So in setting that up, you get H2PO4 1 minus concentration times hydronium, concentration over phosphoric acid's concentration. This is set equal to the Ka. So when I plug in my x's and so forth, this is still our same kind of general setup, x squared over 5.0 minus x, and then I show me what? Neglecting x. And I'm neglecting x because why? Well, one, I don't want the quadratic equation, but there's a reason I'm allowed to even consider it. Huh? Weak acid, meaning the K value is small, it's less than 1, right? It's pretty small. If I have a K value greater than 1, I'm not going to neglect x, okay? So don't forget, we don't always neglect x on other types of problems. So in setting this equal to 7.5 times 10 to the negative third, everybody solve for x for me. And we get point what? 10849 or 649. Okay, I'm just gonna leave it right there. Okay, this is molar, and who is this x pertaining to? Oh, hold on, I didn't actually. Yeah, hold on. You guys tell me your answer. I forgot to put the x value. Times 10. 0.1. Okay, I'm just looking at Darcy. Okay, so this is the molarity of which ion of interest. Okay, and H2PO4 1 minus. So that is actually the concentration of both, because both of those are represented by x. Now to find the pH, we're not going to use the other one, we're going to use the hydronium. So pH is equal to negative log of the 0.1936, and what do we get? Say again. 0.71. I'm good with that because it's 126. Okay. So this is supposedly the pH after the first deprotonation. And then we have these other ions that we can calculate their concentrations of once we know x. So we have a question that's asking us to calculate all these concentrations of all these ions, all the conjugate bases, and whatever. So we kind of have our start, but now we're going to do the second the subsequent Ka. Okay. So we're not going to start with phosphoric acid. We're going to start off with what? H2PO4 1 minus plus water to make what? HPO4 2 minus and hydronium. And this will be Ka2, which the value is given to us. I'll scooch back up there in a second. But unfortunately, maybe fortunately, I actually know two ion concentrations already. Since these two are known now, you must use this data in the icebox. So where does this value go? Initial for this guy. Water doesn't matter. Do I know this ion concentration yet? No, it hasn't even been formed, so I'm going to have a 0 there. Has hydronium been formed? Yes, it's already in solution, because this is all in one big O beaker. Like the first deprotonation occurs, we make the first conjugate base and hydronium. This is already present in solution. All right, so now we go through and allow for this particular ion to undergo its deprotonation by subtracting X, adding X, adding X. So we get 1936 minus X, X, 1936 plus X. So you might already see some simplification that's going to occur, but let's run through the whole process. So this is a Ka2. So our Ka2 value was, thank you, 6.2 times 10 to the negative 8. I don't know if I copied this question for you. Okay, and this is equal to what expression? So these two ions over this ion, right? So I'm not going to write that for a moment. So plug in your X value or your equilibrium values here. X times 0.1936 plus X over, and then we show the process of, okay, we want to neglect the, which X's do we neglect? Oh, sorry, that is minus. That's a minus, but go ahead. Which ones am I neglecting? The added and the subtracted ones, right? So that's 0, and that's assumed to be 0. So now we can really simplify, right? So we have X times 0.1936 over 1.1936, which we can now do what with those? Cancel those out. So X is equal to 6.2 times 10 to the negative 8, which was the Kp or Ka2 value. This X is equal to what concentration? Just the HPO4 2 minus, because that's this guy. So this X is equal to this ion. So I'm going to look for a significant change in hydronium. So I already know hydronium concentration from the first deprotonation is 0.1936. And then just a smidgen more is released in the second process, that much. Is that 10 to the negative 8 going to impact this number? No, like very, very minimally. So I can guarantee you the pH is not changing very much from its 0.71 pH that we initially found. You can even try to calculate it, but it's not going to change significantly. And I'll tell you why. Like, I mean, you're obviously seeing this is a low pH. This looks like it's a strong acid, right? But we know this is not a strong acid. Why is this pH so low? It's like super concentrated. 5 molar is something crazy. Like, we don't even use 5 molar. Like in our labs, like very rarely would we ever. So it's a pretty high concentration, which is why it's making a significant amount of H pluses. Okay, so to keep on going, last one. Let's take our ion, so the second conjugate base that's made, and let's run it through its deprotonation. So HPO4 2 minus plus water yields what? Phosphate. Okay, we have totally wiped all the H's off of that. And hydronium. Okay, what about initial values do I already know? So I know biphosphate, which is this guy, to be what? 6.2 times 10 to the negative 8 molar. I don't care about water. Do I know phosphate at all initially? No, because it has not even formed yet. And do I know hydronium initially? Yes, it's the 0.1936 plus this little bit of an X, but it's not going to impact my number because it's such a small value. So that's still 0.1936. And then I roll through ice. Allow this to deprotonate where it can. Minus X plus X plus X. 6.2 times 10 to the negative 8 minus X, X, 0.1936 plus X. And then, does anybody, I can scroll up. What was that Ka value? 4.8 times 10 to the negative 13. Thanks. And then applying all the equilibrium values here. X times 0.1936 plus X over 6.2 times 10 to the negative 8 minus X. What do I do to make my life simpler? show the neglecting of x. So now it's going to be some math, but then we will solve for x. So you'll take Ka3 times 6.2 times 10 to the negative 8, and then divide by 0.1936. So by moving your integers or your numbers that way, we're going to solve for x. Ready when you are. Go. Louder. Negative 13, 19. So, significant amount of H plus made, right guys? No, come on, this thing is like super teeny. So our H plus, I'm sorry, this will be phosphate. The phosphate ion is nearly not even there. It's such a small amount. That's phosphate. The H plus, or the hydronium, has made a little bit more in the second and then a little bit more in the third deprotonation, but it's not significantly enough to actually affect pH. So pH is still where it was at 0.71. So it's more tedious than hard, I think, but it is very important that you understand how we're taking conjugate base, allowing it to undergo a deprotonation step, and then taking this conjugate base, allowing it to undergo a deprotonation step. And you always know how many you're going to do based on the polyprotic nature of it. Can I move on? Yeah.
Which factors do you use?
For which one? So the value of this one will be we'll actually go back and plug in the concentration of X here. So we'll do 5.0 minus that, and that would be the value for the phosphoric acid. And then this one, we won't use the X value because we'll actually go through, I mean, it actually might still be that initial X value because it's such an insignificant amount of X we found here. So you literally will use the equilibriums at the last time you saw that ion. So you take 0.1936 minus that X, which won't do any damage to that number, so it's the same. And then this guy will be probably still 6.2 times 10 to the negative 8 because that value of X is so teeny tiny. So that's going to be that concentration. And then phosphate will be the X we just found last. Hydronium, all those X's we added were insignificant, so it should still be that. Yeah.
Will there ever be a time when there is a significant change?
Yeah, with sulfuric acid, because that K value is not so teeny tiny. It depends on the initial concentration, but it could still be impactful. So I usually look to see if it's going to make an impact. Mainly, like that was 10 to the negative 8, so that wasn't going to touch my initial numbers. This one would be a large enough value would make a change. So just assess that at the time. Yeah. Yeah, you would say the overall completed, after all the deprotonation steps that occurred, that new pH would be what you did after adding the H pluses that you sequentially got more of. But this one, we saw up front, it was a teeny tiny change that wasn't significant. Good questions. More? Okay, yeah.
We have to do 5% for each of them.
Okay, we really should do 5% rule all the time. But sometimes our brain's like, okay, I can 100% tell that this is not 5% of 5. Like, you can do some of the math in your head. Because it would have to be like 0.25, I think, to be 5%. Because 10% of 5 is 0.5, right? And that's way less than the half of that. And then certainly negative, 10 to the negative 8 is less than 5%. So on some of them where you're able to mathematically figure it out, others you should be calculating to verify. You'll notice that I don't always show it, but we should be showing it more often than not. Okay, so that was the Sol version. Speaking of, there's our sulfuric one. I'm going to wait to do that one though. I want to show you guys the part that actually, this part that's on your note sheet, because this is where we get into, can we determine if somebody's acting acidically or basic as it's compared to water, and how can we find the K value that's associated with that type of reaction. So, the steps that are listed here are going to be how you approach this. So write those down for yourself, and I'm going to be utilizing those as we go through this little exercise. So I can give you any reaction with an ion, with an acid, with a base, and I'm always going to show it with water in some way or form. So water might be in the reactants or water might be in the products, but water is our main focus because water is amphoteric. It can act as an acid or a base. But if you look at how the ion that it's interacting with is behaving, you can then decide if you're working with a Ka or a Kb. So we are looking at the behavior of the ions, or the behavior of the non-water species. So once we look for water, we see how the ion that it's interacting with is behaving. Is it acting acidic or acting basic? And we'll know if we're utilizing a Ka or Kb. And if this is a reverse reaction, meaning water is in the product side, if you have water, I'm going to say reacting in the reverse manner, you flip your K value. So that's what I'm going to show through like, I think there's 10 of these. Give me a thumbs up when you're ready to go for this first one. Okay, so look for water. We see it's on the reactant side. Boom, right here. How is this ion bicarbonate interacting with water? Okay, so draw, and this is, I like to draw the arrows just to show myself what's happening. It is, and the way you find that out is not only like just looking at this ion, but you're looking to see how it ended up. So it accepted an H+. So if you're an acceptor, you were called a what? You were called a base. You're acting basic. So with water, this is acting basic. So I already know I'm going to have to find a Kb. Okay, now this ion is not truly a base. It's bicarbonate. It's an ion. So it's the conjugate base of who? Carbonic acid. So how am I going to find this Kb? Okay, so I must find Kb from Ka of carbonic acid. Now, is this, now, we're dealing with polychronics, right? Is this going to be the Ka1 or the Ka2 of carbonic? Ka1, because this is the first exchange of an H+. So there's carbonic acid and there's the one less H of a version of it. So this is the first deprotonation, which is Ka1. So you're saying find Kb from Ka1, which means to do Kw over Ka1. And I'm actually going to call that Kb1 just so we're on the same page as I'm still writing the first deprotonation. All right, that was fast. Let's do the next one a little slower. Where's water? Product. Okay, automatically I know I'm going to have to reverse this. So I'm thinking about how water is helping this ion react. So this is just the process that I found to be successful with this. You can do it other ways, but this is successful. So how is this ion interacting with water? Okay, it's accepting an H+, so it's acting as a base. Okay, so I'm going to put reverse over here just because I know this reaction is flipped. It's acting as a base, so I must find the Kb, but then I look at these two ions and I see that this is not the first deprotonation of carbonic acid, this is the second, because I can see I'm now down to the carbonate phase, which is no H's. So this is going to be a Kb2. Now it's not just Kb2, because Kb2 would show carbonate on this side, forcing water to give it, or to deprotonate and so forth. So because it's not just simply Kb2, I'm going to show it inverted, because that's what reverse means. Remember that reverse means to invert your K value. You flip it. Remember that? So it's 1 over K. So that means that this is going to be Kb2 raised to the -1, which is 1 over Kb2, if you'd like to write it that way instead. But this is still carbonic acid in a way, right? So how am I actually going to find Kb2? From Ka2, right? So I have to use Ka2, so that's 1 over Kw divided by Ka2, which that looks messy. I don't like this. So how could I modify that? Ka2 over Kw, right? So it's like 1 over 1, and you do copy dot flop and flip things around. It's just Ka2 over Kw. So what we did was we saw water was a product, so we knew we were going to have to invert, meaning the reverse reaction was applied, which is why instead of having Kw over Ka, we have Ka for Kw. Now these values of Kas, they're up on the top of the board here, but they'd be given to you, so you could actually truly calculate the K applicable here. I'm just setting them up because you guys can math. Like you can plug in your phone. Okay, where's water? Okay, reactant, so we're sticking as it is. How is water interacting here? It's receiving an H+, so you're acting as a what here? Okay, it's acting acidic. So this is a Ka. And which Ka of carbonic acid is it? Yep, this ion and this ion represents the second deprotonation process. So this is Ka2. And now that we can just look at this reaction, like it's pretty obvious. That's the bicarbonate species interacting with water to make carbonate, which is showing the second deprotonation of carbonic acid. So you can look at that and say, oh yeah, I knew that was a Ka, and now I know it's a Ka2. There's no modification needed here. This would be a value that would be provided. So that is it. Are you picking up my puzzle pieces here? It's not intuitive all the time, so that's why we're walking through the process. So take a minute to do 1, 2, 3. We'll skip the water. And try the water one for a second. Try those next 4. Just the one you're on. We're going to try to review these before we go. We have less than 5 minutes left here. So the first one, let's just shout out the answer first. Go. What say again? 1 over Ka2. Good. So you're seeing that water on the product side, so you're saying flip. So you already know you're going to have to inverse this K. So I'm just raising it to the -1 power. You saw the water interacting with bicarbonate in a way that bicarbonate was acting as an acid. So if you're acting as an acid and then your counterpart is just the second deprotonation step, so it's going to be not the first but the second, so we have a 2 involved, Ka2. So 1 over Ka2 would be the most appropriate way to write that. Next one, shout it out. Ka whatever. K1 over Kw, or Kw. So your water, again, is on the product side. We're flipping it. This is acting as an acceptor. So it's acting at, right? Yeah. So it's acting as a base, and then you can see the production of its counter ion. So this is the first version of bicarbonate, so this is going to be a combination of Ka1. So hold on. Water is acting, that's acceptor. So I need your KB. Oh, your answer is truly correct because we have KW involved, sorry. So looking for, it's going to be called a KB1 inverted, but it's kV is calculated by taking KW over KA1, but since we're inverting this, this is going to be KA1 over KW. Is that what you guys said earlier? Okay, just making sure. This one? 1 over KW. So it's weird, but you saw water dissociating, but not in the forward direction, the reverse direction. So that's why it was 1 over KW. And then last down here, this is just the first deprotonation step. So this is water here, carbonate acts as an H donator, so it's the acid, and it's the version that has the first 2 ions and salts. So it's not the second deprotonation, it's the first. Okay, so let me modify what I'm expecting here. Okay, I know some of you guys need to finish up 1 through 8 problem set of salt hydrolysis. So I've talked to you a lot in 3 days via me and videos and practice. You know how to do all your acid mixtures, base mixtures, acid-base mixtures, weak acids, weak bases, and salts. That was a lot in 3 days. So we have to practice all those together because there's no longer any segregation between those types of problems. So the salt hydrolysis homework problem set 1 through 8 was supposed to get you started on identifying the type and going, okay, I see this is the type of problem, here's how I solve this type. So you have to type them first, like determine this subset of type of problem you're working with, and then approach the problem solving process. So what I'm looking for Monday is, for sure, these 2 FRQs, one's 1990 and 1997, they'll be in your packet. And problem set 1 through 8, your salt hydrolysis problem set. Some of you guys already got started on the map 2 equation writing. We will do that. I'm not going to have you 10 days, so you'll be guys for free. But if you want to go ahead and work on that, absolutely can. Because next week we're going to do some labs, we'll do some lectures, and then we'll do buffers, which is the last part, that's the base equilibria, and then we'll do like 3 labs in a row. So we can't do our labs until we know our content. So the back side of this is very lab heavy. That's why you have a lot of your content and lecture and really helps to come stuff up front. Great job, guys. Thank you. Yes.